Great. So our next speaker is Sumit, and he will tell us about the notions of color entanglement. Please.
Thank you. Thank the organizers for inviting me to give this talk in a very stimulating workshop. Very tiring, in fact, last week, but very, very stimulating, no question about that. Okay, so I'm going to give a kind of an overview of something which I've been working on over the past, I guess, 4 years now. And this is a list of papers starting in 2020, ending like a few months ago. And the topic is how to think about entanglement of color degrees of freedom. Now, we know that there are many well-known instances where color degrees of freedom sort of metamorphose into spatial coordinates in large N theories. So we're going to talk about notions of entanglement of color degrees of freedom, which are particularly relevant for this kind of metamorphosis. One motivation is to understand possible connections between entanglement and emergent space where the dual theory doesn't have any base space to begin with. Examples are like the C=1 matrix model, the BFSS matrix model for these zero branes, or the BMN models, dual to PP wave geometries. Or to understand the role of internal spaces which appear in string or M theory, which is sort of inevitable in most realizations of ADS-CFT, but something we usually don't talk about very much. However, regardless of these connections to the holographic correspondence, we will find that we end up with notions which are useful beyond this entire field, in particular to interesting many-body problems, which I'll be very brief about. So we'll start with the simplest example of gauged quantum mechanics of a single matrix. This is a well-known model which was basically solved in the 1980s, early 1980s, by Brezai, Parisi, and Zubair. And the way I write this model is by introducing a gauge field. So there is a covariant derivative of a matrix. I've started out with D matrices, but very soon I'll first give the example of a single matrix with some potential, and the trace makes it gauge invariant. We can, of course, in one dimension, choose a gauge where the gauge field is set to 0. The time goes from -infinity to +infinity, so we can do that. And then the Gauss law constraint requires that the wave function to be a singlet under the remaining time-independent gauge transformations. A naive notion of entanglement of the matrix degrees of freedom could be to consider a subset of these matrices, some subset like this, integrate out over the rest, and talk about the density matrix. Of course, this is problematic. It's not a gauge invariant decomposition, and one of our aims would be to obtain a gauge invariant notion. If the model has a single Hermitian matrix, it's solvable in the singlet sector, as I mentioned, and we can use the remaining gauge symmetry to further fix a gauge where I take the matrix to be diagonal. You make a UN transformation to take the matrix to be diagonal. And as is well known, you can absorb a factor of the Jacobian in this transformation such that the wave functions are now antisymmetric rather than symmetric. So the problem becomes that of a non-interacting fermions. The eigenvalues are the locations of these non-interacting fermions which are moving on a line subject to an external potential. There are n such fermions, so one can exactly rewrite the system using second quantization, using a fermion field. And in this way of thinking, the space of eigenvalues becomes the base space of the second quantized theory. And there is a notion of entanglement between subregions of the base space, which is of the standard form, however, in a non-relativistic field theory. It turns out that unlike relativistic field theory, this entanglement entropy is completely finite. And this is sort of obvious in the fermion picture, but it has an interesting consequence for entanglement in two-dimensional non-critical string theory. The non-critical string theory is dual to a matrix model of this type, of a single matrix, and in something called a double scaling limit, where this parameter beta, which I think I did right, was proportional to n, is taken to infinity. The mu is the height from the top of some potential barrier, and this is a particular combination which is held fixed. In this limit, it becomes equivalent to fermions in an inverted oscillator potential. And for a small enough interval, very far away from a strongly coupled region near the hump of the potential, the result for the entanglement entropy is this formula. In this formula, I have gone from the eigenvalues to something called the time of flight coordinates, q. This is just a change of variables. And I have written the answer in terms of an effective coupling. This, I'll talk more about what this effective coupling is, but it is sort of defined, if you wish, in this way. You can see that there is a beta here. Beta is n. So it's like the 1 upon n being the coupling of the theory at large n, in the large n expansion. The effective coupling depends on the location because of an external potential. The fermions are like d-branes in this string theory, and the entropy which we are calculating corresponds to observables which are used to probe d-branes inside this interval. The propagating modes of the closed string theory are, however, different. They are fluctuations of the density, or particle hole pairs which are excited. And it's sort of well known that the fluctuations of the density of eigenvalues are related to the single propagating mode of the closed string theory by a non-local map, but the non-locality is entirely at the string scale. At zero coupling, therefore, the result would be divergent. At zero coupling, you just set this to 0, and this would be a divergent result. And so the result here, though, as if we think a little bit about it, is perfectly natural from the fermion point of view, is a little bit unconventional from the string theory point of view, because you can see that, as I said, the propagating mode is a single massless field in 1 plus 1 dimensions. If it was just a relativistic massless field, it would be the same log with the same coefficient, but instead of this factor, there will be a cutoff. So it is as if the theory is providing a cutoff which is given just with the string coupling. So from the point of view of string theory, this finiteness of this quantity appears to be non-perturbative. There is a well-known expression for the ground state entanglement entropy of a system of non-interacting fermions, non-interacting non-relativistic fermions with a fixed fermion number, which can be written in terms of a cumulance of the number of fermions in a region of interest. This expansion reads like this, where these objects are basically cumulants of the number inside an interval. A is an interval, psi dagger psi is the number density. You integrate that over the interval. So the various terms of this expansion are like the dispersion of that number and the fourth powers and things like that. So this relates, in fact, this entanglement entropy in these particular systems to some correlation functions of the fermion density, psi dagger psi correlation functions. In fact, it turns out all these terms can be expressed in terms of integrals of the expectation value of the phase space density of fermions, or the Wigner function. And at large n, one can use a Thomas Fermi approximation for that and obtain simple expressions which are just single integrals of Heaviside theta functions. We sort of utilize that, in fact, to obtain exact analytic expressions for large n for the entanglement entropy of a two-dimensional region in the integer quantum Hall effect, which is excellent agreement with numerical answers. The leading term is in fact the connected correlator of the density. Rho is like psi dagger psi. So this is like the connected correlation function with the integrals restricted to the region of interest. So A and B are the two endpoints of that integral. You're just supposed to calculate this object and integrate this from A to B. What happens when we try to do this in the collective field theory of the density variable? When the external potential vanishes, we just have free fermions and put them in a box, periodic box, to make things finite. And you can check that this answer which I wrote from the fermion theory now just becomes a simple answer of the, the interval size, delta lambda, multiplied just by the Fermi momentum. The Fermi momentum for a one-dimensional system is a number density of fermions proportional to the number density of fermions. So this is a finite number in the thermodynamic limit when n goes to infinity, L goes to infinity with this ratio held finite. So in this case, it's a Fermi momentum which is provided in the cutoff. It sort of makes sense because we are treating non-relativistic fermions, and as is well known, if I look at the collective theory of excitations of non-relativistic fermions, those are interacting theories. There is a bosonization which is in terms of an interacting field, and the interactions are basically there because there is a bottom of the Fermi sea, and that is what is getting reflected here. In this case, however, this is a very simple case where the external potential vanishes. It was shown by Nomura and then by Jivicki that one knows how to calculate the exact eigenfunctions and the eigenvalues of the effective theory of this collective Hamiltonian. And you can use, therefore, those exact eigenfunctions and eigenvalues to do this calculation. And when you do this calculation, you in fact reproduce the fermion answer as you should. However, on the other hand, if you try to do perturbation theory, namely a perturbation theory in 1 upon kf, which is the coupling constant here, what you would find is that the answer is divergent to every finite order in the perturbation expansion. This calculation is doable in this very simple case. I don't know how to do this calculation in the interesting case of an inverted harmonic oscillator, where the collective theory itself is rather complicated. The finiteness is in fact intimately related to trace relations of n by n matrices. I mean, if I have n by n matrices, the trace of some power of the matrix becomes dependent on lower powers of the matrices when the power exceeds n. And this construction in terms of exact eigenstates and eigenvalues, which treats this in an exact fashion, plays a very important role in ensuring that the result is finite. However, the result remains finite in the double scaling limit for the inverted oscillator, or for the case of a free fermions, for a finite density, even when n tends to infinity. And I don't completely understand this, and I should just mention that there will be a talk coming up by Gautam where there is an alternative bosonization of the model which incorporates these finite n trace relations in a very essential way. And in this bosonization, this thing directly reproduces the finite answer. As I emphasize that the appearance of Fermi momentum as a cutoff is a perfectly natural from the point of view of the fermion field theory. It's the bottom of the Fermi sea. However, it is somewhat unconventional from the point of view of string theory. In string theory, you would have expected that you get an answer which is finite, and it is finite because the string length is finite. Normally, you wouldn't think as a coupling entering as a cutoff. In fact, the low energy effective action of this one matrix model in an inverted potential is dilaton gravity with a massless tachyon. And you might have expected an entropy which is proportional to 1 upon the square of the coupling. Instead, what this quantity we computed in the singlet sector does not give this leading contribution. It gives a subleading answer, which is the log of the coupling. Understanding how to get, in fact, the leading contribution, I think, will be very important. And my guess is that the reason why we are not getting the leading contribution is because the same reason why we don't understand a black hole in the matrix model. It has something to do with non-singlet sectors. And I think if we understand that well, one will be able to understand the 1 upon coupling square contribution. I should mention there are other ways of defining entanglement entropy in critical string theory. In particular, there are replica type calculations on the worldsheet pioneered by Dabolkar and Ace Numasawa Takayanagi, a lot of recent works by Dabolkar and Moitra, which gives a strong indication that those calculations, those are worldsheet calculations in critical string theory, to whatever extent, I don't understand all the details of the analytic continuation, but there are indications that that answer is finite, but it is finite because of the finiteness of the string length. This is sort of what you expect in perturbative string theory. So how come in non-critical string theory the coupling constant is appearing in the game? And I think it might appear because unlike critical string theory, the worldsheet action has an information about the string coupling. It's through the Liouville wall, because the parameter which sits in front of the Liouville potential is actually related to, in the dual representation, is related to this effective coupling or the Fermi momentum or what have you. Now, I don't know how to do such a calculation. There is no symmetry between the Liouville mode and the other mode in this two-dimensional string theory. But I think if one can figure out how to do a worldsheet calculation, one should be able to see whether this answer is really non-perturbative or whether there is a contribution even from the torus diagram, which depends on the string coupling. I don't know the answer to that. What we described is an example of a particular notion of entanglement of colored degrees of freedom, which goes by the name of target space entanglement. To see this, we need to rephrase the problem in a first quantized formalism. So far, we have been doing something completely conventional. There was a non-relativistic fermion field theory, and we calculated the base space entanglement entropy. In the A equal to 0 gauge, this relates to the notion of entanglement of identical particles, which are fermions in this case. But we would like to aim for actually a completely gauge-invariant notion, which would reduce to this notion in that particular gauge. Going back to the description in terms of the matrix and still saying with a single matrix, consider a set of general operators made out of the matrix and its canonical conjugate with some ordering. And we want to consider now how to think of entanglement in the first, this is like a first quantized description, entanglement of these matrix degrees of freedom in terms of a projection. And the projection we will do in this case is the following. We introduce a matrix valued projector, which is defined as follows. There is an integral over a real number x, and there is a delta function with the matrix sitting in that integral. You can immediately see that in a gauge, when the matrix is diagonal, what it does, it picks eigenvalues which lie in the region A and gets rid of those which are not in the region A. And that's the physics of the problem. The projected gauge-invariant operators are obtained by taking this and sticking in the projection operators in an appropriate way. The expectation values of these operators are evaluated by a reduced density matrix with an associated von Neumann algebra. Note that this projection is explicitly in color space. These projector matrices are inside the trace. So they sort of directly deal with the color degrees of freedom. To see what this means, let's consider the case again of a single matrix where the matrix is diagonal. And we consider an operator where, like trace m to the n, which just now becomes a sum over the eigenvalues raised to the n. It is easy to see that, for example, if I take just two particles and an operator which involves the cube and calculate the expectation value of the projected operator, it splits into two terms. In the first term, both the integrals are over the region A. In the second term, one of the integrals is over A, the other integral is over A prime, A complement, which is the complement of A. What this shows is a general result that the Hilbert space breaks up into a sum over sectors. And in each sector is labeled by the number of particles which are living in my region of interest. And each term in the sum is in fact a direct product. The entire answer can be written in terms of a reduced density matrix, and here is an explicit expression for the density matrix in terms of the wave function, as you can easily check. This density matrix I've chosen not to normalize because the trace of this density matrix should give just the probability to find some number of particles in the region of interest. The full density matrix is therefore block diagonal in these sectors, and the full density matrix is of course totally normalized because the sum of probabilities has to be equal to 1. I should mention that there are other useful notions of reduced density matrix, one of which was actually mentioned in the previous talk, and an analogous quantity for that is something called a k-body density matrix in a system of identical particles, which apparently quantum chemists use a lot. What that object involves is an integral over some number of the identical particles to obtain a density matrix which evaluates all k-body operators. And there are sort of generalization of those two matrices. The difference between this and what I just discussed is that these integrals are over the entire space and not, not restricted to some spatial region of interest. And as was already mentioned in the context of holography, this is the notion of entwinement. Before going on to the case of multiple matrices, let me mention one interesting fact. The whole point of recasting a second quantized base space entropy as a target space entropy in the first quantized formalism can be useful in many body systems because there are many body systems where one knows the wave functions in terms of the particles, but the description in terms of a second quantized formalism is sometimes missing or difficult. Famous example is the Laughlin wave function. In these cases, it can be written sometimes in terms of interacting, highly interacting second quantized fields, but that calculating entanglement is very difficult in such cases, whereas a calculation of target space entanglement doesn't really care. I just give you the wave function and you just go ahead and do a calculation, which could be hard. We're sort of experimenting a little bit for a class of integrable models, Calogero-Sutherland model, where wave functions are known. This model has the property that there is a parameter in the model. At one end of that parameter, these are free bosons. At the other end of the parameter, these are free fermions. And we have some preliminary sort of numerical results which show the interpolation between these. That was just an aside. So let's now come to multiple matrices. What is remarkable is that the way we posed the problem of a target space entanglement is sort of trivially generalizable to multiple matrices. So what we do is the following. If there are some number of matrices, which are here denoted by xi, you consider some Hermitian combination of these matrices, which I denote as f of xi. If f of xi could be like x1, it can be x1 squared plus x2 squared plus x3 squared minus r squared, or any combination you like. Then you introduce a projector, which is like that. And again, this is an integral over the real line, and this is a matrix valued operator, which is this exactly this combination. And again, as you can see, what this projector does, that in a gauge where this Hermitian combination of the matrices can be diagonalized, what this does is pick up those eigenvalues which lie inside this interval, which is given by A. Once again, the projection is inside the trace. So this is exactly what I just said. For example, consider the case when this f of xi is just x1. So what this means that in this gauge, x1 is diagonal, pi1 is diagonal, and the remaining symmetries are wild transformations which permute the eigenvalues as mixes up the off-diagonal elements. There is a remnant u1 to the power n which acts non-trivially on the off-diagonal elements and which need to be imposed on the wave function. Once again, there are sectors which are labeled by the number of eigenvalues of x1, which I call labeled by k, which denotes the number of eigenvalues which lie in the region of interest. What does this projection do to other matrices? If I look at a matrix x2, that is not diagonal in this gauge, but you can easily see what this projection does. The projection was introduced in a completely gauge-invariant fashion. In this gauge, what this projection does is to pick up a k by k block of this matrix. However, I don't know what I meant here. What I meant is, however, there is no restriction on the values of these matrix elements. There is only a restriction on the values of these eigenvalues. So those matrix elements can go over anything. It's only the eigenvalues which are restricted to a particular region. And then, of course, to maintain gauge invariance, you have to sum over all sectors. There is an important aspect which I didn't mention, is the fact that a crucial role is played by the Gauss law condition on that matrices. This, I think, Ronak's talk will deal with a lot with that, so I'll not talk anything about it. This was pointed out in this paper by Hampapura, Harper, Jonathan is here, and Lawrence, and Frenkel and Hartnell. And without doing more, let me just say that on general grounds, one expects that for multiple matrices, since it is entangling in square degrees of freedom, we expect to get an answer which is proportional to n square. In fact, this paper, they did a Born-Oppenheimer approximation, and the result is consistent with this expectation. You could also consider a constraint which looks like this. Now, this is not very easy to deal with, but it turns out that you can do a matrix analog of a polar decomposition. And in that matrix, using a singular value decomposition of the matrices, and in this matrix analog of polar decomposition, you can frame the problem and write down explicit expressions for this quantity. I should also say that the notion extends trivially to field theory, where we put the same constraint is imposed at every point in the base space of the field theory. But there are other exotic possibilities where you use a base space constraint and a target space constraint, and this is an area which is relatively unexplored. What is the meaning of this in the dual theory? The variables xi are like the degrees of freedom of n d0 branes in some number of dimensions. In states where these branes are very far and well separated, one can approximately associate the diagonal elements as locations of the branes and with the off-diagonal elements representing massive open string states. Target space entanglement then becomes some form of base entanglement. However, in other interesting states, like the bound state of ND0 brane, which is dual to the IMSI geometry, this interpretation runs into trouble because the whole size of the bound state scales as n to the power 1/3. So even though it is doing some notion of bulk entanglement, its connection to usual gravitational entropy is not clear at the moment in our minds. I'll pause for any questions before I go to the next part of the talk. Okay. So I'll now turn to something different. Now for something completely different. Okay. I'll talk about a different notion of entropy, which we'll eventually see has also got to do with some color entanglement, but not obviously so. And this has got to do with the fact that we want to understand whether there is a notion of an entanglement which is associated with a region of internal spaces which appear in holography. Now, in holography, the ADS space seldom appears by itself. It's always connected, comes with some internal spaces. And what the internal spaces do is they geometrize some internal symmetry of the dual theory. Well-known examples are ADS 5 cross S5, ADS 4 cross S7, or the D1, D5 system. So we will begin to answer this question, whether there is such a notion, by starting in reverse. We will ask, is there a meaning of the area of a RT surface, which instead of being anchored on some subregion of the boundary base space, but anchored on the internal space, in some subregion of the internal space? So the picture sort of looks like this. This is like a torus, this is like a sphere, and you take some cap of the sphere, and you take this RT surface, which is completely smeared over the other spatial directions except the radial direction. Does this thing conceivably have a meaning? This question was asked quite some time ago by Molabashi, Shiba, and Takayanagi, and by Koch and Uleman. And there is an interesting fact about these such RT surfaces, is that if I want such a surface to end on some arbitrary cap, you can't do it unless you keep a finite cutoff. In fact, you can look at this problem, and what you find is as you remove the cutoff, all these surfaces go and end on some kind of minimal surface on the sphere, in this case, the equator. In fact, there is a theorem by Graham and Koch in a rather different context. In the following, I will always keep a cutoff, and you'll see that this cutoff keeps entering in my discussions. To get an idea of what this quantity evaluates, we took a different spin on this problem. So what we did is we looked at cases where such product space geometries appear as infrared geometries of higher dimensional ADS spaces. There are many well-known examples of this. I mean, the Reissner-Nordstrom, extremal Reissner-Nordstrom black holes or black branes. There are a whole class of magnetic branes where you can put a magnetic field in the boundary theory. And for example, the theory can flow from an ADS 5 to an ADS 3 cross R2. And the reason why we want to do this is because in the UV, we know what we are calculating. It's a standard RT surface, which is anchored on some subregion of the boundary of the UV theory. But in the IR, that subregion becomes a subregion of some directions which are split off from the space-time and have become an internal space. So maybe if we think hard about it, we will arrive at some kind of understanding of what this quantity evaluates. So we did a lot of examples of this, of various kinds, and the general lesson of all these examples, which I'll not go through, is the following. Here is an illustrative example of some asymptotically ADS4 space-time going into ADS2 cross R2, like a Reister-Nordstrom black brane. What you find is that when the region this region, which is in the XY plane, it's a strip which is extended in the Y direction with a finite size in the extended in the X direction with a finite size in the Y direction, is a standard base space region of the UV field theory. By the time you come to the IR, these two directions strip off and becomes a part of an internal space. So what you find is the following, that when this size is large compared to the scale of this dimension changing RG flow, then there's a natural way to extract the piece of the area of the RT surface lying in the IR region. And the reason why you can do that is, if you look at this picture, which is quite representative, is that those RT surfaces typically go in bang straight till it reaches the region which can be approximated by an IR geometry. Now, this thing is a bit subtle, depends on individual cases, but that I think is a general lesson. Now, this setup therefore provides a natural candidate for the set of operators which are involved in this discussion. Consider, for example, a product space which is like this. There's an ADS piece and there is an internal space which can be compact or not compact. And what we are going to think about are, in this theory, the base space is this X, which includes the time, and this I'll call the internal space. The primary operators of the dual theory are therefore labeled by quantum numbers of the isometry group of this internal space, like the arc charge, arc symmetry for the ADS5 cross S5. I'll just denote them by L and M, but you shouldn't always think that this is a sphere. This could be anything you like. Those operators have the property that their conformal dimensions actually depend on those quantum numbers in this particular way. This number curly L is the eigenvalue of the Laplacian on this manifold. Now, if this is the IR geometry of a higher dimensional ADS space, these operators in the UV are simply harmonics of standard operators in the UV dual theory, where this part merged with the ADS part to form the UV geometry, which is a higher dimensional ADS. In the UV, if you look at the fall off of the fields near the UV boundary, it goes as some power of z. Z is the Poincare coordinate. That power is independent of L and M. However, if you put a holographic screen in the IR geometry, which is somewhere in between, that power depends on delta L and therefore nu L, and that is the major change that has happened as you flow from the UV to the IR. Consider now an operator which is constructed out of this by hand. I mean, I'm not purely talking in this geometry. And by hand, what I do is I take those operators, multiply by an appropriate, those operators have different dimensions. So in order to be able to add them, I need a scale. And I use the UV scale epsilon, which is the UV cutoff of the theory. and multiply it by the analogues of the spherical harmonics on the internal space. The proposal then is that the RT surfaces we are considering measures the entanglement entropies which are associated with these operators with the internal coordinates y restricted to the region of interest. This is what clearly happens in the flow geometries. Where there is an UV, which is a higher dimensional radius, because it is precisely those operators which have flown to the operators of the IR theory. When this is not the case, we think it's reasonable to speculate that this continues to be so in the cutoff putative dual, and operators of this type, and this proposal was in fact first made by Karch and Ullmann, we sort of realized that in the case of flow geometries and made it more believable. Are these operators local in any sense? To begin with, to probe this question, which is a difficult question, let us calculate the two-point function of these operators. So the two-point function can be obtained from the conformal two-point functions of the primary fields. So you can write down an expression, and the interesting thing, actually you can actually do the sum. Can I just few more slides? You can actually do the sum. So this two-point function I have written in the following way. I introduced an u, which is a log of x minus x prime by e. X and x prime are the base spaces of the theory. Y and y prime are internal space coordinates of the theory. And you can express this two-point function entirely in terms of some known expression, which is the Euclidean propagator of a massive scalar field of mass m, where m is this object, which is living on yn. The utility of writing this sum in this way is that you know how it behaves at large distances. In fact, at large distances, what you quickly realize that these correlators cluster, and they cluster at a scale which is given by m. So if the internal space is non-compact, there is always clustering. The internal space sort of gets broken up into pieces, which is of size of 1 upon m. And when the internal space is compact, of course, that is not the behavior. You won't see any exponential unless this condition holds true. What this condition tells you is that the size of the internal space, the size appeared here, has to be large compared to the ADS scale. We have used ADS units, so everything is order 1. Now, this is possible in flow geometries, because in the flow geometries, the size of the internal space is given by the RG scale, which is like a magnetic field or a radius of the horizon or what have you. But in standard examples like ADS 5 cross S5 or ADS 4 cross S7, they are all of the same scale. And so therefore, there is no locality of this type, which might explain some behaviors of this entanglement entropy, which was calculated by Takayanagi and others. Time to finish with a comment. Now, you must notice that the projection which we did by writing operators like this and restricting y to some region is a projection on operators which are already gauge invariant. So this doesn't seem to have anything to do with colored degrees of freedom. This is as opposed to target space entanglement, where the projectors were inside the trace and directly dealt with the colored degrees of freedom. However, this may not be really true. To look at why this is possibly not correct, look at the one basic fact of holography, a la Susskind and Witten, who calculated the number of degrees of freedom of the field theory by calculating the area of a surface which encloses the ADS 5 cross S5 at some value of the cutoff. The result of that calculation with this Bekenstein formula for the entropy is that the number of degrees of freedom goes as n square. LQ is the volume, and Z naught should be interpreted as the UV cutoff. In this expression, there is a power of r to the power 8. This is the area. This r is the overall scale here. And let us write r to the 8 as r cubed times r5. The reason I did it this way, because these 3 powers of r come from the base space of the field theory. These 5 powers of the r comes from the S5. Now suppose, instead of considering all the color degrees of freedom, which is order n square, I consider some fraction of that of the number, which is a fraction denoted by f. Now, since the whole thing is smeared entirely over base space, and we don't have it, this is really my last slide. Okay, and because there are no constraints on the base space degrees of freedom, this restriction of the degrees of freedom must be coming from color. And so if what this tells you, that restriction to some fraction of the S5 must in some way also mean a restriction to a number of colors, although it must be in a gauge invariant fashion. As yet, we do not have a clear picture of the precise way this happens, and we are sort of investigating the Coulomb branch in order to get a clearer picture. I'm at the end of our talk, so let me conclude by saying that one of our aims has been to explore if there is a notion of entanglement wedge covering a sub-region of the internal space, and how this encodes a division of the color degrees of freedom. It's a difficult thing to explore, but we do believe that it's going to teach us a lot about how the holographic correspondence works, and I think it's essential in understanding holography, and an aspect which is relatively unexplored. And my purpose of giving this overview talk is to first to give a prelude to what Ronak is going to talk about. He's going to do a much more concrete result in this subject, and also to encourage you to think about these interesting questions. Thank you.
Thank you so much. So are there any questions?
Yeah.
Yes.
So in your definition of target space entanglement, you had some arbitrary function f, which appears in the projection operator. Is there some canonical choice of that, or what do different choices correspond to?
So the rough idea is that, these xi's are like the target space of zero brains in that theory. So, I mean, you choose some region of the target space that it's a function f of small xi, where xi are now coordinates, and you associate that restriction in the target space to this matrix function f of xi. So it depends what question you are asking. If you are asking a question about this region, you pick a particular function. If your question involves asking what the d branes on one side of a partition is doing with the other side, you take that function to be some x1 or something like that. But of course, as I emphasize, this connection is not really completely kosher. I mean, it depends on the on the wave function in a way.
Jan?
Since these color entanglement structures might be useful when you want to probe sub-ADS scale locality and so on, do you have any wild speculation on how you could use these ideas to build a tensor model like Mera or so that is valid on sub-ADS scales? Because most of the tensor models have the problem that they are not valid below the ADS scale anymore.
Not really, but I mean, since these are internal degrees of freedom, one could sort of model it by some degrees of freedom which are connected by tensors. So maybe there is a way of doing that. We haven't really have any concrete thoughts along this. But that is a way to go in a way.
Actually, I have a comment on that. So Alex Frenkel wrote a paper in July which basically said that the web of d-branes that Sumit drew is actually, you can think of that as a tensor network for the internal space.
This is the paper I didn't read. I'm sorry, I'm too old for that. Okay? Oh, then you don't need this.